join today's seminar. My name is Chang. Today we are inviting Dr. Viola to present his work on the how plants scavenge energy from the wind to remain airborne. So this topic is a very interesting topic. I heard about him like about a few years ago in the APS. I remember the talk about the dandelions that really, motivated me a lot in the past few years during my PhD study, because I myself is also working on the bioinspired engineering. And so today, before we start the presentation, I really want to have a brief introduction about his background, so you can know better about him. I summarize his work, his materials into a few sentences. So here I will going to have a very brief introduction, and then I will give Dr. Viola some time at that time to present his work to us. So Professor Viola is a fluid mechanics and bioinspired engineering expert at the University of Edinburgh, a distinguished visiting professor at Tsinghua University, and a fellow of INA. So he has over 64 journal publications and more than 250 public outputs. So because of that, he received numerous awards, including the University of Edinburgh's COVID-19 Hero Medal and also multiple INA distinctions. Professor Viola investigated vortex interactions across multiple disciplines, and he was awarded the ERC Consolidator grant for his work on the dandelion inspired drones. So today we're going to hear some details about these projects, right? So let's welcome Dr. Viola to present his work. Yeah.
Thank you. That is very nice, very polite. It's really a pleasure to be here, and thank you very much for taking the time to listen to this talk. When I prepared the talk, I realized that perhaps I haven't been very fair in presenting the title of the talk, because I pretend that I'm going to explain you a lot about how plant seeds fly, but the reality is that I'm going to tell you a lot about how what we have learned about the flow physics of the models of plant seeds. So perhaps what I should have write is how we have learned that we can scavenge energy from the wind by studying models of plant seeds. That would probably be a more appropriate title. So I hope you can see my screen. Now I'll move it to presentation mode. You see it in the presentation mode? Excellent. And the other thing that I would like to mention, even before starting, is that, of course, I'm not presenting just my work. This is the work of a number of people that have worked on this topic, and I've been honored to work with them. And the first one is Chandan Bose, who have done most of the simulation you will see today, and who is a senior research fellow in our group. And then Kohol Kumis, who precedes him as another fellow researcher, and Maddy Sal also from the biological side. Kohol and Maddy, now they have their academic position, and Chandan is moving to Birmingham very soon. There are also a number of PhD students on the second line, of co-investigator in the third line, an external and internal collaborator in the last two lines. So all of these people come way before than me. I just have the pleasure actually to tell you about what we have collectively found together. And I will also tell you about the motivation for this. I'm not sure, maybe I should take this one away. So I will also tell you a second about the motivation for this work. And in this case, my personal motivation has always been the fact that we can try to mimic nature and to have something flying as efficiently as, for example, the dandelion seed. And if we could do that, we could actually have sensors that fly in the environment and collect information, they report back, and what they really could do for us is they can monitor the environment, and most importantly, now that we know that we have already destroyed a good part of the environment, we have to take actions to try to fix the damage we have done. But what we have to do is to be able to monitor the effect of our actions in terms of trying to fix what we have damaged. And when we do this, we can think about doing this with normal drones, but large drones have the problem that they need power and they have a limited range and they have a limited endurance, and eventually they also have a significant environmental impact per se, for example, in terms of the noise and so forth. You cannot have hundreds of drones that actually are continuously hovering around your head, because that would have a significant impact. So you need to go smaller and smaller in order to try to have sensors that they are fundamentally with zero impact on both nature and what you do. Of course, they have to be biodegradable, but this is one of the aspects that is probably easily addressable, as I will show you in a minute. But the problem is that, as soon as you try to do that, you realize that as soon as you go smaller, it becomes harder and harder to fly. So here is some examples. So when you try to take a drone and you scale it down, you go, for example, in the Harvard RoboBee on the left-hand side, and the endurance is just a few seconds. So here in this case, for example, you see the little wires coming from the bottom is because this is actually powered from external source. You can potentially power it remotely, but you need to the endurance will be very short. In order to have a high endurance, instead, you can have this great invention that was made more than 20 years ago at Berkeley, where actually you can see that the one in the middle is a mole of smart dust. And they are so small, sub-millimeter, that they effectively, the Reynolds number is of the order of 1. And so they fall so slowly that they remain afloat and they never fall. But as soon as the dimension of the mole becomes of the order of the millimeter cube, then it doesn't work anymore, because the Reynolds number approaches a few tenths and the mole fall quickly. So if you want to have a camera, for example, if you want to have some type of effective long-range communication, you cannot do that anymore. And so for that reason, we have developed this device on the right-hand side, which we call the Dandy drone, because it's dandelion-inspired drone, which actually takes inspiration from the aerodynamic performance of the dandelion in order to be able to remain afloat for a long time. And the reason why this device on the right-hand side is so efficient is I try to explain it in this plot here. So here on the bottom, you see the Reynolds number. And on the vertical axis, you have the vertical force that a device that is freely falling in the air can generate. So on the very far left, you have the smart dust. As I said, as the Reynolds number approaches 1, the vertical force becomes very large, and that's because the drag goes very large. And so you can actually fly relatively well when you are in this regime here. Now, the drag, however, reach about a minimum at Reynolds 100, then it remains constant, which means that if you are at the order of Reynolds 100 or more, and you just simply try to fall, you fall like a stone, and that's not efficient at all. It doesn't allow you to remain in the air. So that's when you start to use lift to try to remain afloat. And this curve here represents typical lift over drag ratios, which are observed in nature. So if you now consider that you have the lift to be exploited, you can have some horizontal velocity. And in doing this, you can compute how much you would be able to generate by exploiting lift in terms of vertical component. And this is what the purple curve is. This is what drones do. And it's clear that there is this gray region in the middle where the purple curve is too low to provide sufficient upward force to actually remain afloat for a long time. And so that's why it's so difficult for a RoboBee to remain afloat, and why it's so inefficient from a power consumption point of view. But this curve here instead is the dandelion seed, and even the dandy drone. And the drag coefficient here is so large because it exploits permeability. So it's effectively what the dandelion does is using filaments to generate a very large wing, which is 90% empty, and therefore it provides sufficient upward force with a relatively low weight. So by taking inspiration from the dandelion, what we envisage is to have these clouds of small sensors which are inspired by the dandelion and fly in the air that transport They are completely transported by the wind, collect information, and then report back. And in order to report back, there are many technological ways that we're exploring, but that will be part for a different talk. But if we want to do this, if this one is the motivation, then we need to understand a number of things from the point of view of the physics. And the very first question that we need to ask is, what is the simplest model of this dandelion? Then we need to wonder how this model, that in our case we figured out being a disk, how this disk will fall in the air. And then we start, of course, with quiescent flow. So we let it fall in air that initially is just stationary. But then we start having gas, and then we look into what is the effect of the gas. And the last problem is actually the most interesting one for me, is because it's the one that is completely unresolved at the moment. So in this talk, I will touch very quickly about some of the past research. I will show you about the diaspora of the dandelion. I will show you what we found in the past about the flow around the dandelion, and how the same flow feature, which is called the separated vortex ring, can be generated around the porous disk. Then we will look into some new results, and here we'll look into what is the kinematics of the free-falling disk. We will shift to plates simply because the simulation of disk are very time-consuming. So most of the most recent research has been done on plates, and then will be transported into disk. And so then I will show you the differences between the kinematics of plates and disk. And eventually I will show you the research that is, to me, the most exciting about the effect of horizontal gas on free-falling plates. So the dandelion, when we speak about the dandelion, we speak about this small diaspora. Diaspora is nothing else than all the appendages that goes together with the seed when they fly away. So in this case, you can see here this diaspora here. It clearly doesn't fall, right? I mean, there's some strange reason why it just simply doesn't fall. And if you drop it in the laboratory, it falls at 0.4 meter per second. So it means that it should fall actually in a couple of seconds. Should actually be on the floor if you drop it from your height. But actually it doesn't, as you can see in this video. It just simply doesn't fall sometimes. And the reason why this doesn't happen is quite interesting and intriguing. So what we found is that in our previous research is that if you hold the dandelion still and you let the flow flow through at the same velocity as it would normally fall, the dandelion generates the separated vortex ring that you see here on the top. It is a separated vortex ring because if you look at it in 3 dimension, what it is a sort of a donut where the flow recirculates inside. And what it is quite spectacular about this separated vortex ring is what I'm telling you in a minute. But before explaining you how we investigate what is spectacular about the separated vortex ring, let me just show you what is our methodology. Here we develop a vertical wind tunnel. In this case, it's a very simple wind tunnel of a size of less than 0.5 meter by 0.5 meter in terms of test section. And then we develop a number of dandelion-inspired bodies, which we can fly in the wind tunnel. The most importantly, as you can see here, what they normally are is that they are filamentous structure. So the permeability is not uniformly distributed, but it's radially distributed. But what our numerical finding shows is that the radial distribution is actually not critical. And then you can attach some sensorial components to it. And as I mentioned before, if this one is up, if the motivation is the one that I told you before, clearly this has to be biodegradable. And these bodies here, for example, this one here is entirely biodegradable. So they can actually either biodegrade or they are self-consuming. So by the time that they transmit the information, they will burn themselves. So this one here on the left and on the right, there are 2 models tested in the vertical wind tunnel. they have, on the right-hand side, they have the same Reynolds number as the dandelion and the same porosity as a dandelion. And as you can see, you have the same separated vortex ring as on the dandelion. But on the left-hand side, you have a similar model with zero permeability. So zero porosity and zero permeability. So the flow does not flow through here. So that's the reason why we call it separated vortex ring, because this ring actually is a flow feature is completely separated from the body. In an impermeable disk, so in a solid disk, what you will see is that a similar flow features but attached to the body. And more importantly, the Reynolds number here is much lower. The reason is that if you were to go at the same Reynolds number, you would observe this. And this is what makes the separated vortex ring so remarkable. The fact that it's a flow feature that slows everything down. So the flow field just around here on the side of the plate has the same velocity in the two videos. But inside the separated vortex ring, the flow slows down and very gently recirculate. The ability of the permeability of the porosity here, and I will make this distinction in a second, the ability of this flow passing through the plate to stabilize this feature eventually also results in a substantial low pressure at the two centers of this vortex. And so this is associated with some uplifting force. Okay, so let me now show you how we can model this numerically. Well, the simple model of that feature that you have seen is to consider, of course, the continuity equation as written here. And this one here, which would be the Navier-Stokes equation normally, here is slightly written in different terms where we added this component here. This component here is called the Darcy term. And what effectively does is to, instead of considering the porosity, it computes the permeability. So it computes, it's a sort of a sink term that represents the sink of momentum of the flow passing through the plate or the disk. So in this way, with this Darcy term, we are modeling the permeability of the flow. So the permeability is actually defined by this non-dimensional number, which is called the Darcy number, which is the non-dimensional permeability. So the permeability divided by the disk squared. And what the Darcy number does is to represent effectively the equivalent fluid mechanics of the porosity, which instead is a geometrical feature. The other thing we do is that he normally would be normal to see here the Reynolds number, but instead you see this Galilei number. The reason why we use the Galilei number instead of the Reynolds number, which is nothing else than equivalent of the Reynolds number, but scale with the gravitational velocity instead of the terminal velocity. The reason why we do this is because when you take a plate or a disk and you drop it, you don't know at which velocity it will fall. So the Reynolds number is not something you can set a priori. The Reynolds number is the results of the simulation. Instead, you can use the gravitational velocity, which you can compute a priori, and we define it as the ratio between the mass and the density and the diameter squared. And this gravitational velocity is effectively a velocity scale of the gravitational force. And in that way, this one actually is a control parameter that you can set as an input. But the gravitational velocity is also the velocity at which the plate will fall if the drag coefficient was 1 and if the Reynolds number was of the order of 100 or greater. And so for that condition, it means that, in other words, the Reynolds number and the Galilei number are very closely related, and they're always, both of them, of the same order. If the plate is free to fall, then you also have to couple them with the Newton's Euler equation of motion. And what you see here is that if we couple these four equations together, they only depends on the Galilei number, the Darcy number, the mass, which in this case is written non-dimensional terms, so it's the mass divided by rho diameter cube, and the inertia, also written in non-dimensional terms. So we have 4 parameters here. The inertia, we don't consider it because if we consider a uniformly distributed mass, the inertia is fixed. So effectively, we have 3 parameters: the mass, Galilei, and Darcy. So now let's go back to the results. And in this case, we compare the experiments that I've described to you a second ago with the simulation. As you can see that the simulation of can actually represent fairly well this flow physics. There are differences for sure, but a separated vortex ring is captured numerically at the same Reynolds number, where remember that experimentally you have this geometric parameter, which is the porosity, and numerically you have this flow parameter, which is the Darcy number, that represents the permeability. So now we have learned that we have a numerical tool that is capable to capture this physics. So what we use it to explore the parameter space. So the first things we do is that we look at what is the effect of the Reynolds number. And without making the presentation too boring with long plots, I thought to show you some pictures. And here you can see clearly that as the Reynolds number increases, the effect of the separated vortex ring is actually to shrink or to move downstream, even more importantly. So the stagnation point on the downstream has moved just a little bit, and the stagnation point on upstream has moved a little bit more. So there's a translation, there's a shift of the separated vortex ring and relatively shrinking in sides. But the real shrinking happens when you increase the Darcy number. So if you make the disk more permeable, here you make the separated vortex ring smaller and smaller. Now this is actually quite interesting because it means that with these 2 parameters, you can entirely control both the position and the dimension of the separated vortex ring. So that's actually quite cool. Okay, but these were actually fixed bodies. So what happened when you let them fall? When you let them fall, you actually discover that the kinematics is very, very complex, meaning that there is a variety of kinematic solutions. In this case, for example, you have that 2 different ways of falling at the same set of parameters. So we have the same non-dimensional mass, Galilei number, and Darcy number, and yet in one case, the plate is fluttering, and the other case, the plate is tumbling. Now, there's a lot of studies about the different modes of falling of impervious plates. We believe this one is going to be the first one for permeable plates. But more importantly here, we would like to focus on which is the parameter that actually makes the fall steady. Because when we look at the dandelion seed falling, we know that it falls steadily. So for example, in this case, what we realize that if you decrease the Galilei number, that's one way to make the fall steady. So if you want to apply it to fall steadily, one of the things you can do, you can decrease the Galilei number. In fact, the other way is to decrease the non-dimensional mass. So lowering non-dimensional mass or Galilei number, like in the one in this figure here, is one way to increase the stability. And here you see, for example, the vertical coordinate versus the horizontal coordinate that allows you to actually plot the trajectory of the plate as they fall. And you can see that at Galilei 50, which is the lowest value, the trajectory is just straight, while at Galilei 100, it starts to have oscillation. At Galilei 150, where you have tumbling and fluttering at the same time. Before initially it flutters and then eventually it tumbles and it moves away. Right, but there is another way. There is another way to do this because the dandelion actually operates at a high Galilei number, around 150, and yet it does not tumble or flutter. It falls steadily. So how comes? Well, the reason is that it lowers the center of gravity. That's the reason why it has a lower. The seed is actually attached to a stick under the filamentous pappus. So if you displace the center of gravity lower, as you would probably expect, what you're effectively doing is you change the inertia, which was the other parameter, pre-parameter in our simulations. So now we're actually exploring how to use this inertia parameter. And you can see here is that if you operate at the Galilei number of 150, which is the one of the dandelion, you can, by lowering the center of gravity, achieving a stable fall. And that on the right-hand side is a good representation of the fall of the dandelion diaspora in quiescent flow, so in a flow that is stationary. Okay, so now we move to plates. The reason, as I said, we move to plates is because plates represents nothing else than a two-dimensional situation, as a two-dimensional model with respect to the one that we have just explored. Into the major difference is that the flow is a little bit more unsteady, and therefore the result is that in order to, for example, the transition between a stable and an unstable fall is not in the same values of the parameter space, but the physics remain the same, and therefore it allows you to understand what is going on with the lower dimension and the lower computational effort. So in this case, we explore the non-dimensional mass versus Galilei number, which I also repeat here the definitions for your ease. And we explored this parameter space to understand which are the values where the permeable plate will fall steadily compared to non-steadily. In this case, we don't displace the center. The reason why we do this is because effectively what we want to explore the effect of the gas. But in order to explore the effect of the gas, we would like to go at a Galilei number condition, which is as high as possible to represent the one of, for example, a dandelion seed, but it is also falling steadily. And so in order to do this, in two dimension, we know that first of all, we need to go to slightly lower Galilei number for the reason I explained before. But the other way to do it is also to explore the mass ratio or the non-dimensional mass. So we can in this map here allow us to explore this value here, which has a lower mass ratio than the dandelion, but allow us to go higher in terms of Galilei number without being unsteady. And then I will also show you what happened when you go to this range here, which is at high non-dimensional mass, but low Galilei. Now, just to give you an idea of how to read this map, in the horizontal axis, you have effectively the representation of the effect of viscosity. So here you have a very viscous flow, and here you have a less viscous flow. So if you move horizontally, by changing the viscosity, you only move horizontally in this plane. So on the right-hand side, you have the high Reynolds number condition. On the left-hand side, you have the low Reynolds number condition, if you wish. On the vertical direction instead, this non-dimensional mass, what it does is that it depends only on if you change the density of the flow, you only move vertically, right? So what effectively this one shows you is that on the bottom here, you have a condition where the density is high, and on the top is when the density is low, the density of the flow is low. And so what this effectively shows you is what is the relative effect of the fluid forces compared to the gravitational force. So here you have that the gravitational force dominates, and here you have that the fluid force dominates. Okay, and not by any means not unexpected that when the fluid forces and the viscous forces are high, you are in a very stable region, as opposed to vice versa. You are unstable on the opposite region. Okay, so we now will focus on this green region here, which is stable. But the other thing that we had to do, which I think is interesting to mention, is the numerical tools that we had to develop to do that. Well, if you imagine that you have this dandelion falling or this plate falling, and then when the gas occur, and in this case you have a horizontal gas from left to right, effectively this body will start translating also horizontally in addition to vertically. That requires a domain which is huge. In order to give you an idea, the body itself will move hundreds of diameters. So for all of you who are familiar with the CFD simulations, normally you put your body in the middle and you have 100 diameter is a big size for the domain around that body. In this case, you have that the body moves around by 100 diameter. So it makes your computational domain huge. So in order to address this, what we did is we developed a non-inertial frame of reference simulations, which is effectively, what we're doing is that we're solving the equations only in this small square, and which is this one here on the right-hand side. And the plate is inside of the square. And the kinematics of the plate is fixed, is given by a fixed gravitational velocity vertically and a fixed gas velocity horizontally. So the domain falls at the gravitational velocity, which is prescribed, and then it moves horizontally at the velocity of the gas. And then we solve only the Navier-Stokes equation, well, the Darcy equation inside of this domain. But we need to make, of course, a correction for the fact that we have fictitious forces. Now, what it is interesting here is that in terms of the vertical flow, this is easy enough, right? So you basically, the only thing that you have to do, because it falls at a constant velocity, you supply a vertical flow through your domain. So this is what you normally do, for example, when you test in a wind tunnel, right? If you have in the vertical wind tunnel, we supply some vertical velocity, which is equivalent to the terminal velocity of the body. But for the horizontal velocity of the gas, it's slightly more complicated because it's a gas. So it's a non-constant velocity. So this velocity here will vary over time. So what happens is that if we take our momentum balance equation, in this case, was given by the Darcy equation, and if we write it in a non-inertial frame of reference, we would need to add all of these terms, where this one is the acceleration of the domain, and this one is the angular velocity of the domain, and so forth. However, because the angular rotation is null in this case, our domain is not rotating, our domain is only translating horizontally. It means that all of these terms go away. So the only thing that we have is this term here. This term here is like a source term in the momentum equation. And because the source term is actually uniform spatially, it varies over time, but it does not vary in space. That means that it acts as a body force. And this body force is, again, does not vary over in space, and therefore is exactly the same as gravity. You typically can neglect it because it doesn't make any difference to the fluid and torque on the body. The reason for this is fundamentally Archimedes' principle, which says that the forces provided by the pressure gradient due to this body force is perfectly in equilibrium with the body force itself. So that's the reason why you don't need to model gravity. And in the same reason, you don't have to model this term here. However, let me just go one step more on this. What you see here is that if you were to model that term, you would effectively generate a pressure gradient across your domain, is shown here on the top, a pressure gradient across the domain, which will provide nothing else than a horizontal hydrostatic pressure. That's what it would really do. So we neglect that one. We don't need that one. We don't neglect it, actually. We don't need that because it doesn't change anything in the forces. But when we solve the Newton's Euler equation, that's different. Because here you have the mass multiplied by the acceleration is equal to the sum of the fluid forces acting on the body and the gravitational forces. So if you have to add again the non-inertial terms, you will end up with all of these terms. Then all of those are in red are those that we don't care because they're related to the angular velocity of the domain that is 0. But you have these additional terms. So this one is really what it turns out to be the effect of the gas. Now, the reason why I wanted to highlight so much this way to write the equations, because it's extremely insightful on the physics. What it basically tells you is that if you imagine what is happening when a horizontal gas hit a free-falling body, what this horizontal gas do is nothing else than giving it a push. See, this one here is nothing else than an acceleration, which is the acceleration of the wind, that multiplies by the mass of the body gives you a force. And this force is the force due to the horizontal gas. So the only thing that you can see as the effect of the horizontal gas on a free-falling body is a horizontal push. So that helps a lot, I believe, to understand what is going on. So going back, the parameters now that we have to identify are this UG, and which is the velocity of the horizontal velocity of the wind. We actually need the time derivative of it. So this time derivative of UG, because our UG has this shape over time, so it's a cosine function. So basically the flow initially is, horizontal flow is 0 initially, and then suddenly starts to move, and it increases with a very sharp cosine ramp, and then it remains constant over at a certain velocity. So by defining the gas ratio and this interval along which the velocity increases from 0 to the gas ratio, with these two parameters, we define entirely what our gas acceleration and therefore the gas force is. So we have these two parameters. So here we go, an example where we have an example set of these two parameters. So we have a gas ratio, so this one should be gas ratio of 0.9 and a time interval for the gas of 2.5. And with these other set of parameters that now you're very familiar with, you can see the vertical velocity versus time. So here's a plate that is dropped from a 0 velocity and initially has 0 velocity, so it starts accelerating and falling down. It falls down to a velocity that it's about -1 in non-dimensional terms, which means that it's falling roughly at the gravitational velocity, which is what we expected from what I told you before. And then at this time here, the gas hit it. So this one is a plate that is falling, initially steady, then it starts falling faster and faster. It reaches a constant falling velocity. At that point, it's hit by a horizontal gas. And you see that the velocity fluctuates a little bit, and then it turns back to what it was before. And here we plot two different curves to persuade you that our non-inertial implementation is correct. And so we plot the two curves and we show that there is a good match between the two. The small differences are due to the fact that when you go from a non-inertial to an inertial frame of reference, you need to change completely the grid and the domain, and so the solutions are never identical. So here is an example of what you could see from a non-inertial frame if you observe a plate falling. So when the plate moves upwards, what it means is that it is still falling down, but it is falling at a lower velocity than your frame, so a lower velocity than the gravitational velocity. And when it is perfectly stationary, it means nothing else that it is falling exactly at the same velocity of the frame, which means that it's falling at the gravitational velocity. Now, why all of this is interesting? Well, it is interesting because what we actually find out that if you set a nice set of conditions, and particularly in this case, as I mentioned before, I'm going into this range where we have an IBiM value but a low Galilei number. In this region here, if I give it a strong enough kick, in this case, actually, I provide a constant acceleration. If I give it a sufficiently high kick, you see that this UZ now, that start from 0 and it turns and it goes to about -1, then it actually becomes positive. It means that this body, by effect of simply a horizontal push, is going back up. Now, this is, to me, extraordinary. You need to imagine this effect. You have the dandelion seed, and you have dandelion plant in your hand. You blow it, and what you see is that by simply blowing it horizontally, this object moves upwards. So here is the explanation. So when you have a free-falling body, if you hit it with a horizontal velocity, you can generate a temporarily very significant upwards trajectory. And if you have to plot this one in the horizontal versus vertical coordinate, so this is effectively what you see here is the spatial coordinate with a fixed from the point of view of Earth, so from the observer that it could be the person blowing the dandelion, you will see that the dandelion might fall vertically initially, then it's hit by a horizontal gust, it fluctuates, and it moves up. It moves up, and only after a long period of time, it will actually start falling down again. And here you see that the dandelion starts falling at its own terminal velocity together with the horizontal motion of the wind. All right, so in conclusion, what I wanted to convey today was that we have indeed persuaded ourselves that we can model the aerodynamics of the dandelion diaspora with a porous disk, and the distribution of porosity is not important. You can actually model also with a uniform distribution of permeability. It's not important is the wrong term, but what I mean is that a uniform distribution of permeability is sufficient to generate the key flow features that we observe on the dandelion, which is the separated vortex ring. And we have learned how to control the separated vortex ring, and by means of two fundamental diameters, which are the Reynolds number and the non-dimensional permeability, the Darcy number. When this body is free falling, we found out that it falls steadily if you have a low enough Galilei and non-dimensional mass number, and if you have a high enough permeability or Darcy number. Most importantly, the horizontal gas, in general, the effect of a horizontal gas on a free-falling body is to slow down the descent velocity. So the descent velocity of the free-falling body never increases, always decreases by means of horizontal gas. And actually, it might decrease by so much that it becomes positive. So it is normally negative, is pointing in, is falling down. The magnitude decreases by so much that it can actually be reversed, and it can actually point upwards. And so this body can actually be uplifted by a simple horizontal gas. Okay, these are the main observations that I wanted to tell you. If you want to know more, this is the logo with our website, but perhaps some of the references here might be of use. I should mention, and Chandan wanted me to mention, sure, that the last two papers are two working papers, and so they're not published yet. And so we'll be very grateful if you instead can wait to read them at least up to after tomorrow, when we'll update a new version, and then we will let you know when the paper are finally published. Thank you.
Okay, thank you so much. Thank you for your impressive talk. I'm sure like our audience really enjoyed the talk. So we still have a lot of time, and so let's start the Q&A session. So for audience, do you have any questions? If you have a question, please raise your hands. Hmm?
Hello.
Hello. Yeah, you continue.
Yes.
Yes.
Yeah, this is Mr. Bisang from China. It is a very fascinating talk regarding the fly of Deadly. I'd like to know, the drag of these small structures, how is related to the Reynolds number. This is the question I'd like to ask. Thank you very much.
Right, so thank you. So this is the drag of the dandelion, is the drag coefficient of the dandelion versus the Reynolds number. So you see that at very low Reynolds number, it tends to very high values. And then it plateaus at Reynolds number greater than 1,000. Eventually, it has to reach the same asymptote as the drag coefficient of an impermeable plate. So it will plateau at Reynolds number greater than 1,000. But what is perhaps more importantly is to observe that you have a factor of 5, 6, or even 10 with respect to an impermeable body. Now, what it is important to observe here is that this drag coefficient is based on the projected area. So the dandelion we saw, we can model it as a disk. But this one is not, but in the drag coefficient, you divide the force by the area. Now this one is not the area of the disk. This one is the area of the filaments of the dandelion.
Yes. Regarding this scaling law of the drag, and of course you have a plotting, but do you have any formulas or any predictions regarding this scaling law or drag related to the Reynolds number?
So I do not have an analytical formulation that allows me to justify these values.
Okay,
I don't.
Thank you. But thank you very much. It's a very beautiful work. Thank you. Thank you very much.
So Professor Viola, so I do have a question about from this discussion. So you mentioned you modeled the dandelion as like a small disk. That's why I saw in the presentation, right? But for real dandelion, I mean, shape is like it's not like smooth arc, like it like a diameter like a smooth like arc. It's not like a perfect cylinder, so perfect disk. So I wonder how this kind of like the outer like line shape will change the fluid dynamics. Have you ever like think about that problems? Yeah.
So in two of the papers in the last slide, we discuss about this, and the key things is that so if you imagine the angle between, can you see my cursor? Can you, right?
Yes, I can see that.
Right. So you see this filament here with respect to the vertical direction. So if you consider this angle, here, of course, first of all, is different for every filament. Okay, fair enough. But roughly it is 90 degrees, all right? And but what the point is that actually the dandelion changes this angle actively on purpose in order to change its aerodynamic characteristics. Now, the fact that it is actively and on purpose, it's a bit ambiguous here. But the point is that what the dandelion does is this: when the moisture in the air is greater, and so there's more humidity, the humidity is higher, the dandelion, we imagine, perceive it as a favorable place where to land. And what it does is that actually closes up and it falls more rapidly. While instead, when it is dry, it will open up. And so the drag changes depending on the level of humidity. Now, what we observe in one of the papers that we've written that it's in in the last slide, is that this is important for takeoff. So the dandelion decides basically to increase this drag by increasing the angle to 90 degrees when it's dry, because when it is dry, it's more likely that there will be larger gas fluctuation, that it will be able for the dandelion to be transported farther away. While wind gas are more likely to be lower when the level of humidity is higher. And so we have shown that by changing the angle of the pappus, of the filaments, it actually changes the amount of the distance by which they are transported, because of the selected day in which they will detach.
Let's see. So this is definitely more smarter than I saw. I saw they don't change the shape. Looks like during evolution they found a way to change the structure because the moisture of the air, right? Okay.
Yes.
So yeah. So any other audience have questions? Okay, so I saw someone like post a chat message in the chat. I will just read it so you can answer that. I mean, you can check the chat too. So if I
actually I cannot. Maybe I should stop share. Maybe here. Hold on. Chat.
Okay,
yeah, I found
it. So
okay.
if I understand it correctly, this is a two-dimensional. If so, can you comment about three-dimensional effects considering the real number is not very low? Yeah.
So these simulations here are 3-dimensional. So every time so probably I should have clarified it. But when we say disk, for us the disk is 3-dimensional. Okay, so the disk is an axisymmetric body as the one you see here. Here you see only half of it, but the disk is actually this axisymmetric body, which has is effectively a circle with some thickness. But then what we did is that we simply moved to at this point here we moved to plates, and plates are 2-dimensional. Here is when we start moving into 2-dimensional. Now the physics is the same. So all the physics applies to plate and disk are fundamentally the same. The key differences are that the flow is the instabilities are triggered more easily in 2 dimensions, and therefore, for example, when you look at this map, these numbers will be different if it was a disk rather than a plate. So here you see that, for example, at a non-dimensional mass, the Galilei number of 40 is sufficient to become unstable. Most likely for a disk, 40 will still be stable. You will need a greater Galilei number to become unstable. We know from the CFD simulations we have done that at 150 it is stable. It's actually here. At 150 is unstable, 100 is unstable, but 50 is still stable. These are 3-dimensional, right? So this point for a disk, so this line will be shifted here for a disk. Have I addressed the question, Liha?
Hello. May I ask you a question again?
Absolutely.
Yeah, sure. Forward.
Yeah. Regarding the simulation, of the 3D structure, of the filaments, do you have to consider the turbulence modeling or other rather just laminated? So when you do the simulations.
That is a very good question. So this, as you can see from this picture, the flow is very much laminar. So
okay.
This effectively what happened to the dandelion is transported by the wind. And because it has such a low inertia, the velocity of the dandelion is very similar to the velocity of Lagrangian tracer of the flow. So if you had a Lagrangian tracer in a turbulent simulation, dandelion will basically follow very closely, but not exactly, this tracer. The differences in velocity between the tracer and the dandelion are small, and they will form laminar flow. They are small enough to be laminar, but not large enough to be turbulent. So the flow perceived by the dandelion is effectively a laminar flow. And as you can see that here, if you yeah, I suppose. So we don't need in the CFD simulation, we don't need to run turbulent simulations until we don't want to see what is the transport of a dandelion in a turbulent stream. That's the only time where we have to do turbulent simulation. And in that case, we do DNS.
Okay.
Okay.
You see this dandelions, the papas, there is almost a number of filaments with different size and also diameters. So these three structures, filaments, what about the interactions when they're flying? You know, the flight, you know, the flexible filaments. Because the modeling you use, and I think that will be different from the real dandelions, because the filaments is so fine that they actually flag almost like a deformation during the flight.
Actually, you can see in this figure here, in this video here, that the filaments do not deform at all. So of course, when I say at all, I can only say to the extent to which it is visible. So they will have some displacement. It's smaller than what we can see, but it's certainly smaller than the fluid scale that would matter. So as you can see from this video here, which is a real video with a real dandelion, the filaments are perfectly steady. So the forces on the filaments are too small to provide any meaningful deformation to the filaments. The reason is because even if they are so small at that scale, because of the scaling law, they will actually are extremely stiff compared to what they would be if you scale everything up. So they're actually very stiff. So the interaction between the filaments there is an interaction, but the interaction is made is a fluid interaction. It's not the interaction between the filaments moving. And the fluid interaction can be effectively, if I summarize what the fluid interaction is in 2 words, the filaments are sufficiently small that the Reynolds number of the filaments is about 1. And because the Reynolds number of filaments is about 1, the boundary layer around the filament is very thick. And so the flow struggle to flow through the filaments because of the very large boundary layer. And that's what results in the separated vortex ring, which effectively is nothing else than a feature which has the scale of the collective effect of all the filaments, right? So it does not have, the separated vortex ring does not have the scale of the one filament, but have the scale of the group of filaments. So actually it represents the interaction of the filaments.
Okay, thank you. And this is an amazing video. Thank you. It almost like as you said, that the filaments almost like a stick, very stiff, but then they're holding the separate attaching vortex. This is amazing because initially I imagined that filaments will be changing shape during the flight. Oh, this is a really amazing phenomenon. Thank you very much for your very deep investigation. Thank you.
Thank you.
So yeah, we go to a few more questions. So Julia said, how to choose the thickness of the porous disk?
Okay, so this is a very interesting question, and it's interesting because the question that have been asked today, they're very similar to the question that I can see a number of investigators besides our group are actually exploring by their own. So the effect of the thickness of the porous disk, for example, has been investigated by others. And what you can see is that it does have an effect for sure. So it does change. So if you make a parameter studies and you change the thickness of the disk, you will see that there will be some differences. But the fundamental physics that I described today into general terms is unchanged. And actually, in the limit of the plate of the disk, the thickness of the disk or the thickness of the plate to vanish, the results as an asymptotic solution, and so effectively all of the, because our thickness is sufficiently small, which is about 1/10 here, is effectively irrelevant. So if you were to halve the thickness compared to what we used, you will see no differences, or virtually no differences, because of this asymptotic solution towards for a thickness that goes to 0.
Okay.
If I address your question, yeah, okay.
I see. Thank you. Thank you so much.
So we have one more question from Zhang Xin from the chat channel. So he said, what's the critical Reynolds number at which the symmetric breaking of the flow occurs?
Right. So yes, so as the Reynolds number increases, the very first things that happen is that the symmetry of the axisymmetric wake breaks down. And I don't have an answer on top of my mind, but I believe that in our paper in Physics of Fluids 2017, I think we provided that information. So it would be Cummins et al. Physics of Fluids 2017.
Okay, great.
So I don't remember out of my mind.
Yeah, that's totally fine. So we're almost running out of time, but I really have one more question I want to ask you.
Sorry, can I just add one thing on this? Apologies, just one more thing.
Yeah.
Of course, the critical Reynolds then depend on Darcy, right? So the critical Reynolds has a fixed value for an impermeable plate, but this critical Reynolds increases as the permeability increases. Sorry.
Okay.
Sorry.
Great. So I have one more question. Sorry. So in terms of the size, because we mentioned multiple times, this is a tiny size, and I noticed on the vision is try to get inspiration from this data line to design the data drones for the environment monitoring somehow in the future. So do you have any comments in terms of the scalability of these kind of findings from the data line? Can we make it larger? Because I noticed from the Bruce number graphic you just showed before, you get if size larger, the drag significantly drop a lot. And do you have any comments in the future? So how can we extend this aspiration to a larger drones for the environment monitoring, something like that?
So I think the answer is very simple to this question, right? So it's this green curve. So the green curve is what you really can do. Then of course, if you try to be a little bit smarter, if you change the number of filaments compared to the thickness of the filaments compared to the width of the filaments, you can have some variations and you can move a little bit from this green curve. But fundamentally, you cannot change by an order of magnitude, and neither you can change the trend. So the fundamental answer is, if you go at Reynolds number 100, that's where you have the maximum gain, because everything else is very difficult, right? So at Reynolds number 100, you can do you have a huge benefit. If you go smaller than Reynolds 100, then anything can fly, right? Because when you arrive to Reynolds number of 1, like your little droplets of saliva that comes out and remains in the air for hours, right? So you do nothing, and just because the drag is high, you never fall. On the other hand, if you go to Reynolds number 1000, you can just glide, and so there's no reason why you should do it. So these are the two extreme, right? So Reynolds 1, no point. Reynolds 100, that's your goal. Reynolds 1000 makes no sense. So you have to stay in the area around Reynolds 100, and the lower you are, for sure, the lower the Reynolds number, the more you stay afloat. That's the answer.
Okay, thank you so much. Thank you for explaining and like a conclusion of the entire presentation. Okay, thank you for spending your time with us. And it is a very lively discussion, like Q&A session. And And thank you for everyone for attending today's seminar. And yeah, see you guys.
Thank you very much. Thank you very much.